Methyl cellulose, MC, is one of the most important commercial cellulose ethers owing to its excellent water solubility, thermoresponsive gelation, rheological behavior, film-forming capability, biocompatibility, and chemical stability. Produced by the partial methylation of cellulose hydroxyl groups, MC has evolved from a simple thickening agent into a multifunctional polymer used extensively in pharmaceuticals, food, personal care products, construction materials, ceramics, coatings, adhesives, and biomedical engineering. Unlike native cellulose, which is insoluble in water because of its highly ordered hydrogen-bonded crystalline structure, methyl substitution disrupts intermolecular hydrogen bonding and introduces hydrophobic domains, imparting amphiphilic properties and enabling reversible thermal gelation. These unique characteristics make MC one of the most versatile renewable polymers for industrial and biomedical applications. Molecular structure and synthesis. Cellulose, the precursor of methyl cellulose, is a linear polysaccharide composed of beta-1,4-linked D-glucopyranose units. Each anhydroglucose unit, AGU, contains 3 reactive hydroxyl groups located at the C2, C3, and C6 positions that participate in extensive intra- and intermolecular hydrogen bonding, giving cellulose its high crystallinity and mechanical strength. During methyl cellulose synthesis, these hydroxyl groups are partially substituted with methoxy, OCH3, groups through an etherification reaction while preserving the linear beta-1,4-glucan backbone. The extent of substitution is expressed as the degree of substitution, DS, representing the average number of hydroxyl groups replaced per AGU, with theoretical values ranging from 0 for native cellulose to 3 for fully methylated cellulose. Besides the average DS, the distribution of methoxy groups along the polymer chain strongly influences water solubility, thermal gelation, and rheological behavior. Industrial production of MC begins with highly purified cellulose derived from wood pulp or cotton linters. Cellulose is first treated with sodium hydroxide to form alkali cellulose, which swells the cellulose fibers and increases hydroxyl accessibility. Etherification is subsequently carried out using methylating agents such as chloromethane, producing stable ether linkages. Careful control of reaction conditions allows manufacturers to tailor molecular weight, substitution pattern, and DS to obtain products with specific viscosities and functional properties. 2 principal synthetic approaches are employed: heterogeneous synthesis. The dominant commercial process performs etherification within swollen cellulose fibers. Because cellulose remains in the solid state, hydroxyl accessibility is uneven, resulting in heterogeneous substitution patterns containing highly methylated domains. These localized hydrophobic regions promote strong thermogelation and are characteristic of commercial MC grades. In contrast, homogeneous synthesis dissolves cellulose in solvent systems such as dimethylacetamide/lithium chloride, quaternary ammonium hydroxides, or NaOH/urea solutions before etherification. Uniform accessibility of hydroxyl groups leads to a more homogeneous distribution of methoxy substituents, producing materials with improved water solubility but generally weaker thermoresponsive gelation. Characterization of methyl cellulose. The most valuable techniques used for characterization of methyl cellulose in terms of the degree of substitution and the molecular weight. Substitution pattern. DS determination can be carried out by C13 NMR analysis to obtain not only the global DS but also the degree of substitution of each carbon, C2, C3, and C6. In the C13 spectrum region between 59.5 and 58 parts per million, Three signals correspond to the methyl substituents at C2, C3, and C6 positions, from low to high field, respectively. The ratio between the integral of each methoxyl signal and that of anomeric signals at 103.8, C1, and 103.2, C1s, parts per million, attributed to 4 linked beta-D glucopyranosyl units unsubstituted on C2 and substituted on C2 by a methoxyl group respectively, allows the determination of DS2, DS3, and DS6 values, and consequently, the average DS proton NMR spectroscopy may also be used to characterize methyl cellulose. The spectrum shows intense signals at 3.48 to 3.47 parts per million, corresponding to the overlapping of methyl protons at C2 and C3, and at 3.31 parts per million attributed to methyl protons at C6. Using H1 integral as reference and the proton integrals for 2-methyl plus 3-methyl and 6-methyl, it is possible to determine DS on C, 2 plus C3, and C6 positions for methyl cellulose. Physicochemical properties of methyl cellulose. The unique performance of methyl cellulose originates from its amphiphilic molecular architecture. Remaining hydroxyl groups maintain hydrophilicity through hydrogen bonding with water, whereas methoxy substituents introduce hydrophobic interactions. Consequently, MC exhibits excellent compatibility with aqueous systems while simultaneously displaying significant surface activity. Its physicochemical properties are governed primarily by 4 structural parameters: degree of substitution, molecular weight, distribution of methoxy groups, and polymer concentration. These factors collectively determine solution viscosity, gelation temperature, mechanical properties, interfacial activity, and processability. The remarkable versatility of methyl cellulose arises from the intricate relationship between its molecular architecture and physicochemical behavior. Unlike most natural polysaccharides, MC exhibits a unique combination of hydrophilic and hydrophobic characteristics, owing to the partial substitution of cellulose hydroxyl groups with methoxy OCH3 groups. This amphiphilic nature governs its solubility, rheological behavior, interfacial activity, thermal gelation, film-forming capability, and compatibility with numerous inorganic and organic materials. 4 structural parameters primarily determine the physicochemical properties of MC. 1. Degree of substitution, DS. 2. Molecular weight, MW. 3. Distribution of methoxy substituents along the cellulose backbone, and 4. Polymer concentration. Collectively, these variables dictate the polymer's performance in aqueous systems and ultimately determine its suitability for diverse industrial applications. Water solubility and amphiphilic nature. Water solubility depends strongly on the degree of substitution. Commercial grades with DS values between approximately 1.3 and 2.5 dissolve readily in cold water, whereas highly substituted materials, DS greater than 2.5, become increasingly soluble in organic solvents. Homogeneously substituted MC generally exhibits better water solubility than heterogeneous commercial products because of its more uniform distribution of methyl groups. Preparation of homogeneous aqueous solutions requires careful processing. Direct addition of dry powder into cold water often forms swollen gel particles that hinder dissolution. Therefore, industrial practice involves dispersing the polymer in hot water, 70 to 80 degrees Celsius, followed by cooling with continuous agitation, allowing complete hydration and formation of clear, homogeneous solutions. Lower critical solution temperature, LCST. One of the most distinctive characteristics of methyl cellulose is its lower critical solution temperature, LCST. Below the LCST, hydrogen bonding between water molecules and polymer chains stabilizes the hydrated state, maintaining solution transparency. Upon heating, hydration of methoxy groups decreases, hydrophobic interactions become dominant, and polymer chains begin to associate. For many commercial MC grades, the LCST occurs near 29 plus or minus 2 degrees Celsius, although the exact transition temperature depends on molecular weight, concentration, DS, and the presence of salts or cosolvents. Electrolytes generally reduce the gelation temperature through salting out effects, whereas alcohols and glycols increase it by stabilizing polymer hydration. This reversible thermal response distinguishes MC from conventional hydrogels, such as polyvinyl alcohol, agarose, and gelatin, which typically gel upon cooling rather than heating. Thermoreversible gelation. Thermal gelation of methyl cellulose is entirely physical and reversible, occurring through hydrophobic association rather than covalent cross-linking. Gel formation proceeds through a two-stage mechanism. In the first stage, occurring between approximately 30 and 50 degrees Celsius, localized association among highly methylated chain segments produces a weak, transparent pregel in which viscosity increases gradually, while polymer chains remain highly hydrated. During the second stage, typically above 55 to 60 degrees Celsius, microphase separation occurs as polymer-rich domains become concentrated and water is partially expelled from the network. Strong hydrophobic interactions generate an opaque fibrillar gel, possessing substantially higher elasticity and mechanical strength. Cryogenic transmission electron microscopy and small-angle neutron scattering have revealed fibrillar networks approximately 15 nanometers in diameter that provide the structural framework responsible for the high stiffness of the strong gel. Cooling gradually dissociates these hydrophobic associations, allowing complete recovery of the original solution. Hysteresis during gelation. A characteristic feature of methyl cellulose is thermal hysteresis. The temperature required to dissolve the gel during cooling is generally lower than the temperature needed for gel formation during heating, resulting in non-overlapping heating and cooling curves. This hysteresis arises from the slow rearrangement of fibrillar aggregates and gradual rehydration of densely packed hydrophobic domains. The phenomenon is particularly relevant in biomedical formulations and food processing, where repeated temperature cycling can influence product stability and performance. Rheological properties. The rheological behavior of MC is central to its industrial importance. Dilute aqueous solutions below the LCST behave approximately as Newtonian fluids, with viscosity depending primarily on molecular weight and concentration. As temperature approaches the LCST, intermolecular associations induce shear thinning behavior, and above the gelation, temperature oscillatory rheology shows the storage modulus, G', exceeding the loss modulus, G', indicating the formation of an elastic gel. Molecular weight increases chain entanglement and zero shear viscosity, whereas higher polymer concentrations promote formation of interconnected three-dimensional networks above the overlap concentration, C*. Increasing DS generally lowers gelation temperature and strengthens hydrophobic interactions, while slow heating favors formation of more homogeneous gel structures. These rheological characteristics make MC particularly valuable in extrusion-based processing, pharmaceutical manufacturing, ceramic forming, cement formulations, and additive manufacturing. Surface activity of methyl celluloses. Unlike most polysaccharides, methyl cellulose exhibits pronounced surface activity. The amphiphilic polymer chains adsorb spontaneously at air-water, oil-water, and solid-liquid interfaces, lowering surface tension and stabilizing dispersed systems. Surface adsorption occurs through orientation of hydrophobic methyl-rich regions toward non-polar phases, while hydroxyl-rich segments remain hydrated. Equilibrium surface tension of dilute aqueous MC solutions typically decreases from approximately 72 millinewtons per meter for pure water to about 50 to 55 millinewtons per meter, demonstrating substantial interfacial activity. Unlike conventional surfactants, methyl cellulose forms relatively thick, adsorbed polymer layers that provide steric stabilization against particle aggregation and droplet coalescence. Consequently, MC functions simultaneously as emulsifier, foam stabilizer, protective colloid, suspension stabilizer, pigment dispersant, rheology modifier. These properties are exploited extensively in food emulsions, latex paints, pharmaceutical suspensions, ceramic slurries, and cosmetic creams. Film-forming properties. Methyl cellulose readily forms transparent, flexible films from aqueous solution owing to extensive intermolecular hydrogen bonding during solvent evaporation. The resulting films possess high optical transparency, smooth surface morphology, moderate tensile strength, excellent oxygen barrier properties, relatively low grease permeability, good adhesion to numerous substrates. Because film formation requires only water as solvent, MC has become increasingly attractive for environmentally friendly coatings and biodegradable packaging. The incorporation of plasticizers such as glycerol, sorbitol, polyethylene glycol, or citrate esters further enhances flexibility by reducing intermolecular interactions between polymer chains. Water retention capacity. The high water retention capacity of MC results from hydrogen bonding between residual hydroxyl groups and water molecules combined with restriction of water mobility within the polymer network. This property prolongs workability of cement mortars, improves hydration of Portland cement, prevents premature drying, enhances bakery texture, retains moisture in cosmetics, stabilizes pharmaceutical gels, and improves printability of bioinks. Water retention generally increases with molecular weight because of greater chain entanglement. Thermal stability. Although thermoresponsive in aqueous solution, dry MC exhibits good thermal stability during normal processing. Thermal degradation proceeds through moisture loss below approximately 120 degrees Celsius. Cleavage of methoxy substituents between 250 and 320 degrees Celsius, degradation of the cellulose backbone above 320 degrees Celsius, and eventual carbonization at higher temperatures. Chemical stability. The polymer is chemically stable over a broad pH range, approximately 3 to 11, and its ether linkages are considerably more resistant to hydrolysis than cellulose esters. As a non-ionic polymer, MC is relatively insensitive to ionic strength and exhibits excellent compatibility with salts, fillers, and numerous water-soluble polymers. Applications of methyl cellulose. Methyl cellulose is a versatile, non-toxic, and non-digestible polymer utilized across various industries due to its unique thickening, gelling, and binding properties. The most important producers of MC are Hercules, Incorporated, Wilmington, Delaware, USA. Aquilon Division with Benecel A and Culminal, Dow Chemical Company with Methicel A, and Shin Etsu Chemical Company with Metallose SM. A variety of such cellulose derivatives exists mainly with different MW or viscosities in aqueous solution, but only a slight variation in the degree of substitution. In the Benecel and Methicel cases, the characteristics are given by a specific code, A for methyl derivatives, a number indicating the viscosity, in millipascal seconds, of a 2% solution in water at 20 degrees Celsius. This number for viscosity is followed by a letter C, indicating times 100, and M, times 1000. The letters LV refer to a special low-viscosity product. Methyl cellulose is provided as a white powder, or sometimes as coarse particles, in pure form and dissolves in cold, but not in hot water, forming a clear viscous solution or gel. Food industry. Identified as E461, MC acts as an emulsifier, thickener, and gelling agent. It improves the volume and texture of bakery products, reduces fat pickup in fried foods, and prevents ice crystal growth in frozen desserts. It also stabilizes emulsions in dressings and serves as a fiber source in dietetic products. Pharmaceutical and biomedical. MC is used for the controlled release of active ingredients in tablets and as an edible, plant-based alternative to gelatin for capsules. Medically, it serves as a lubricant for dry eyes, a saliva substitute, and a bulk-forming laxative to treat constipation or diarrhea. It is also employed in cell culture media and cryopreservation. Construction and ceramics. In construction, MC is a critical additive for cement and gypsum-based materials like tile adhesives and plasters. It enhances workability, water retention, and adhesion. In ceramics, it ensures uniform thickness and better flow. Additionally, it serves as a rheological modifier in paints to prevent sagging. Cosmetics, adhesives, and agriculture. Cosmetics. MC provides the characteristic thick consistency for shampoos, liquid soaps, and lotions. Adhesives. It is used in bookbinding and wallpaper pastes, providing a flexible bond that can be cleaned with water. Agriculture. It acts as a suspending agent for pesticides and fertilizers, helping them adhere to seeds and waxy plant surfaces. Other applications. MC is used for sizing in paper and textile production to prevent oil or water absorption and serves as a colloidal stabilizer in PVC polymerization and various resins. Finally, methyl cellulose possesses excellent biocompatibility and environmental compatibility. It is non-toxic, non-immunogenic, and not metabolized by human digestive enzymes, allowing its widespread use as a soluble dietary fiber, pharmaceutical excipient, ophthalmic lubricant, wound dressing component, and controlled drug delivery matrix. Derived from renewable cellulose resources, MC is also biodegradable under suitable environmental conditions, making it an attractive, sustainable alternative to petroleum-derived polymers in packaging, biomedical devices, and functional coatings.